So with great pleasure, want to introduce Atsushi, who's going to talk to us about revisiting dependently typed programming and multi-stage programming.
Thank you. Thank you for the introduction. And I'd like to thank the organizers for giving me an opportunity to talk about my recent work on dependently typed multi-stage programming. So this is joint work with some of my students, Akira Kawata and Shuntaro Katsuda. So let me start with what multi-stage programming is about. Multi-stage programming refers to programming that involves manipulation and execution of program code. And typical popular applications are runtime specialization, and it's also useful to implement DSLs. You parse an input of DSLs and generate code from the DSL programs. And multi-stage programming, MSP, languages are supposed to support such programming. And popular features include quasi-quotation as in Lisp or eval constructs. So let me show one MSP language, which is MetaOCaml. MetaOCaml is an extension of OCaml with MSP features. And so Walid Taha implemented the first version of MetaOCaml, and later Oleg Silev had a re-implementation of MetaOCaml with a different name. And so, but they share the common mechanisms. Well, let me go through this easy example. So this 1 plus 4 surrounded by angle brackets are quotation. So it represents not 5, but the AST of expression 1 plus 4. Actually, for those who know MetaOCaml a little bit, MetaOCaml needs dots around brackets, but I removed it just for easy readability. And so C1 is bound to the AST of 1 plus 4, and the type of C1 is int code that represents it's a code, and the expression has type int. Okay. And then now I define function double C, and again this is quasi-quotation, and inside quasi-quotation you can use tilde for unquote. So it double takes an C, and so it unquotes C. So C is supposed to another piece of code, and this function splices the code into another piece of code, which is times 2. So the type of double is int code to int code. It takes code of integer expression and returns another code of integer expression. And when I apply double to C1, then you get this AST. Okay, this is easy. And you can run this code to get the value of the expression. Okay, so that's the MetaOCaml. And the type system of MetaOCaml is based on Hindley-Milner because it's ML. And it has code types, as I described in the last slide. And this is important to guarantee the well-typedness of the code inside brackets. Okay? And the old version of MetaOCaml had another device called environment classifiers. And they are useful to, they are introduced to guarantee that eval succeeds. In particular, for eval to be applied successfully, the code inside brackets should be closed. Otherwise, there may be unbound variable errors. So, but it's dropped in recent versions of BER MetaOCaml for various reasons. So now the goal of our work is to introduce dependent types for such a language. Okay, and if you know dependent types, you can imagine what kind of benefits the introduction will bring. So let's show a kind of hypothetical extension of MetaOCaml with dependent types. So consider we are implementing vector library, and this vec-add gen takes an integer, and it generates a code for vector addition of the specialized for the designated length of the for the vectors. So it takes so this type is a special. So it's a pi type. It takes integer n and returns this code. But okay, I should explain what vec-n is. Vec-n stands for the types for vectors of length n. Okay, so vec-add gen takes n as an integer and returns the code of functions that takes two vectors and returns another vector, and the length of these vectors will be the same, n. So if you apply this function to 3, then you get this type, vec3 to vec3 to vec3. So it means that it's a code of a function which takes vectors of length 3, and it will return another vector of length 3. So ideally, you want to get code of this function, which is specialized to vectors of length 3, okay? And it directly returns another vector. And the benefit of these dependent types is that when you run and apply to vectors, if the length of vector is different from 3, then you will get a compile time error rather than runtime error, which is a great benefit. Okay, so this is what this talk is about. I'm going to explore so-called full spectrum dependent types for MetaOCaml-like languages. By full spectrum, I mean arguments to type constructors like n in the last example. By the way, they are called indices. Expression of the programming language itself, MetaOCaml expression. In some languages, the index language is separate from the programming language itself, but I want to merge with, actually, this is the original dependent types formulation. But, and I'd like to introduce recently developed core type theory for this extension. And I'd like to discuss why full spectrum dependent types may be interesting. It's a pretty much work in progress. Okay, and by the way, so my title includes revisited because there are several old work that try to combine MSP and dependent types already. And as far as we understand, those dependent type systems are not full spectrum dependent types for some valid reasons. Okay, so this is a table of contents of this talk. I would like to start with a simply typed core calculus for MSP, and then extend with dependent types. Okay, this is a core calculus of MSP, which is a simplified version of language called lambda white triangle percent, developed by one of my former students and me. So it's a lambda calculus with bracket, escape, and something called cross-stage persistence. Okay, I'll get to that in the next slide. And types are simple: base types, function types, and code types. Okay. So let me briefly mention what is cross-stage persistence. So it's written %n, and it's an operator to embed a value of the value of m into another piece of code. So you can write a function like this. It takes x as an integer, and since this is a call by value language, x is bound to some concrete integer value. And then this returns a piece of code 2 times %x. So if x is bound to, say, 5, then you will get the code for 2 times 5. So it looks like lifting a value into code, but it doesn't. That's my opinion. So actually, % can be applied to any type, including function type, which might not be lifted easily. So the semantics of % is like this. Actually, it awaits evaluation of surrounding code, in this case, 2 times. So if this piece of code is applied to passed to eval, then you have to generate code. Then you generate multiplication of 2 with this value. That's the semantics of %. So it interacts with eval. So that way, you don't have to have a syntactic representation for every value. So for example, if this is a context expression containing the occurrences of %m, it's passed to run. Then we first compute the value of m, and you get this piece of code. And then run evaluates C of v, removing %. That's the semantics of cross-stage persistence. And in MetaOCaml, % is present, but it's implicit. It's implicitly inserted to variable references, not for arbitrary expressions. Typically, it's inserted to the use of library functions. So if you call, say, list.map inside quotation, that list.map comes with % to refer to library function from inside the quotation. Okay, and so I'm going to talk a little bit about the type system. It has to take into account something called stages, or the number of brackets. So the type judgment form is augmented with at n1 to nk, and the type is augmented with, actually this is not the part of type. The judgment called m is typed, m is given type t at stage n. Those n and I are natural numbers. And for m, n stands for the number of brackets surrounding m. And variables n1, ni for variables represents which stage those variables can be used. Okay, so for example, okay, so suppose, let's start with stage 0, which is the normal terms. And inside brackets, it's stage 1. So x is declared at stage 1. So you can use the x only at stage 1. So inside tilde, unquote, it demotes to level 0. And so, and again, there is a bracket. So inside bracket, it's stage 1. So you can use x. So this expression passes a symbolic representation of a variable to code generator, like double, and splice the result into this function code. But this is ill-typed because x appears at stage 0, not stage 1. Okay, so these are basic typing rules. So these are terms for simply typed lambda calculus, which is not very interesting. Basically, each n forms simply typed lambda calculus. So for application, both terms have to be typed at the same stage. Okay, and yes, when you write lambda abstraction, the stage of the variable has to be recorded in the type environment. Okay? And then things get more interesting when we introduce brackets and unquote. Okay, so bracket is well typed and is given T code if the body of the bracket M is typed, is given T at the one stage up. And the unquote is the opposite. Okay, it's the elimination for code types. And percent promotes the stage of M by 1 for any type. Okay. Oh. So these are examples of valid type M judgments. If X is given declared to be int code at stage 0, then you can unquote X at stage 1 to get type int. And you can add these expressions, and you can when you surround this expression by a bracket, then you get int code at stage 0. And if you abstract by X, then you can get a function code generator int code to int code, like this. Okay. Okay, that's the basic type system, and we are going to extend this calculus with dependent types. So let me show how the type syntax is extended. A base type is indexed by the terms of this calculus. It takes maybe n arguments, and this is dependent function types. It takes argument of type S, and the argument can appear in T. T might be index type, and MI might refer to X. And the T code is as before. So the basic question is how do dependent types and stages interact? So because types include the expressions, and the expression typing, as we saw in last slides, depends on stages. So should type well-formedness depend also on stages? That's the basic question to answer. So let me revisit the vec-add example we saw a few minutes ago. So the code of vec-add gen is going to be something like this. It takes an integer n, and it produces a piece of code that takes whose body is a two-argument functions, and probably generates some efficient code using unquote. But this is a little bit strange with respect to the typing rules I described before. In particular, these two types include reference to n, but it appears inside brackets. So it seems that it violates the principle of variable reference. Variable reference should appear at the same stage as its declaration. Yes. So there are two ways to solve this. In old works, let's consider n as a special kind of variables, which is outside of the language, which is for index language. But we don't take that approach because we would like full spectrum dependent types. So our solution is to use cross-stage persistence to fill the gap between the variable declaration and the variable reference. So vec gen should be written like this in our system. First of all, vec is applied to %n. So n is promoted from level stage 0 to stage 1 by %. And now this is a well-typed, well-formed type of expression. And to reflect this, the type of vec gen is also comes with few cross-stage persistence. And as a result, we have to take stages into account for kinding to check well-formedness of type expressions. maybe. Okay, these are basic kinding principles. So base type constructors like vec can appear at any stage. So it can be used kind of globally. And all arguments to B should be typed at the same stage. And resulting type is well formed only at stage n. That's the principle. So if so for vec-m, vec can be used as a type operator that takes an integer to yield a well-formed type. And if the argument is well typed at stage n, the vec-m can be used only at stage n. And likewise, for T code, since the T is kind of T describes the type of the things inside brackets, so T must be well kinded at stage n plus 1. And but so far so good. But it can be annoying to always distinguish m and %m during type checking. Suppose, so this is familiar via gen, and we have the value of x3 like this. And we'd like this expression to be well typed. Okay, so this is a code generator for length 3, and it applies to 2 vectors of length 3. So actually, unquote vec gen 3 will be given type this one, but the arguments are typed vec 3. So there is a slight gap between the former argument types and the actual argument type. So our solution to this is to sometimes we ignore % for closed expressions. So we introduce term equivalence rule like this. Oh, by the way, I forgot the side condition. M must be closed. Yes, so the gamma should be empty. So this makes this type of expression well typed because vec %3 is equivalent to vec 3. So the rationale for this rule is that if a closed time is well typed at some stage, then it is well typed at any stage. So actually closed type, an expression or a closed type can live at any stage. So that's why we can ignore the existence of %. By the way, the basic assumption here is that base type constructors and constants are given the same kinds and types at any stage. Okay, so this is an advertisement. We developed Lambda MD, which stands for, I don't remember, and with a student. It was presented at Atlas last month. It's a dependently typed extension Lambda white triangle %. It has LF style signature to declare base types, kinds, and types of constants. And it has quotation, the CSP. And I didn't talk anything about eval, but it has features for eval based on another work of mine. But it's kind of orthogonal to this issue, so I omitted entirely. Okay, now I'm going to talk about why full spectrum dependent types might matter. Okay, this question can be phrased like, is there any use of staging constructs, brackets and unquote, inside indices? That's my point here. So the obvious to me, but one possible application is equality types. So equality types takes 2 terms as an argument. So IDMN is type, okay? So it expresses equality of program at the level of type. Okay, so if M is equivalent to N in some sense, then this type is inhabited. There is a term that has this type. And why this is useful? Well, if ID type is inhabited, and if there is some term that includes M1 inside, then you can create another term that has this type where M1 is replaced with M2. So it allows M1 to be replaced M2, and the types expresses the property of program. So it allows, it utilizes the fact that M is equal to N, okay? And so I said equivalent with quotation. By this, I mean, equivalence can be not arbitrary, but you can design different kinds of equivalence at that point. Actually, Frank Fenning studied such different notions of term equivalence in type theory. So he introduced modal type theory with two kinds of equivalence. One is called extensional term equivalence, which identifies terms through computation like beta equivalence and unquote cancels quotation. And so it's crucial for dependent types. So say, yeah, it already appears. We ignored percent, and it is allowed by introducing term equivalence. Or you can have vec of 1 plus 2, which is equivalent to vec 3, and like this. And the other equivalence is intentional or syntactic term equivalence, which identifies only alpha equivalent terms. It doesn't allow any computation. But I think this is suitable for terms inside brackets, because terms inside brackets stands for an AST, and the ASTs don't compute. So it's, I think this kind of term equivalence is more appropriate for code types. So why not just combine these equalities to different levels? So I'm going to call this hybrid equality equal H. So this is the least congruence closed under reduction at stage lower than or equal to N. So below, so we are focusing on N, which is where computation happens. And then N and lower stages computation happens, but the N plus 1 and higher, they are ASTs. So we don't want to allow rich equivalence through beta reduction. So for example, 1 plus 1 is equal to N at stage 0, but not as int code, 1 plus 1. The AST of 1 plus 1 is certainly different from the AST for 2. And these are equivalent because you can beta reduce this lambda and cancel quotation by unquote, and you get this AST by, well, kind of stage 0 computation. So these are equivalent. Okay, so based on this funny equality, we can introduce equality types based on hybrid equality. So how can it be useful? Well, if you can show ID of M and quoted lambda x is inhabited, then it means that M is really code over lambda x, lambda abstraction. Actually, in the this type judgment, M is of type code of some function types. It doesn't. It means that M, the value of M is code of something of function type, but it doesn't guarantee that the body of quotation is lambda abstraction. It might be a big function application that eventually evaluates to function abstraction, but it doesn't mean M itself encloses a lambda abstraction. But this ID type ensures that M is equivalent to AST for lambda abstraction. And okay, so we get a way to specify the form of code by this kind of intentional equality. And furthermore, if you are familiar with dependent pair types, it's kind of existential quantifier, then you can abstract the body of the term. For example, if you have exist X of int code and paired with identity type, M is equivalent to this guy, then this type expresses M is code of an addition of the same integer expression X. Okay, yeah, that's the idea. But we haven't, as I said before, this is a work in progress, and we are working with the theory with that. Okay, so let me close with some related work. The first one, lambda white triangle percent is a calculus for quadratic quotation, CSP and eval with simple types. And actually, there are, as I said before, there are a few studies about dependent types with multi-stage programming. And concoction introduces MetaOCaml with dependent types, but dependent index language is Coq terms. And lambda H circle is an MSP calculus with dependent types, which is again with index language is different from the programming language. And it doesn't have run or CSP. And Berger and Tratt developed program logic for MSP language, but their language is very different from ours in that they can deal with only closed code, and they don't allow symbolic representation for variables to be manipulated. So it's rather different. By the way, I have 2 minutes probably, or I can skip this one.
You can, yeah.
Okay.
This is including questions.
Oh, I see. Okay, so by separate index language, we mean by this. So vec-add in old studies have to be written like this. So cint stands for compile time integer type, and it's erased at runtime, and it's not staged. So it takes integer, and it takes n, which is a runtime value, and int I stands for the singleton type, which is equivalent to I. So n must be the same as I. And it generates a code of this function. And note that vec is annotated with I, not n. So since I is not staged, this is a well-formed type expression. So this approach amounts to a decidable and technically simpler because types are not staged. But you have to think serious about the index language. It's often domain-specific index language. Okay, so we are exploring full spectrum dependent types for multi-stage programming, and it brings usual benefits of dependent types to us. And furthermore, I'm interested in use of equality types based on hybrid equality. It seems to give fine-grained information on the shape of code values rather than the behavior of code values. That's it. Thanks. I take any questions.
Hi. I was wondering if you have anything to say about the consistency of such a system, because normally when we grow it to a dependent type theory, then we'd like to know whether it is normalizing or in some form. Right. So have you thought about this aspect?
Not. We are thinking about that. First of all, if we have recursions and other effectful computation, we have to, we say this is full spectrum dependent types, but index has to be some subset, well-behaved subset of the programming language. But the point here is that brackets are not effectful, so it can be introduced into the index language. And
But I would still expect that there are some complications that happen with this hybrid equality.
maybe.
Because the most of the normalization proofs, you know, they would, I mean, the traditional ones for Martin-Löw type theory, for example, they would certainly assume a more intentional notion of equality, and now you're adding in this this extensional notion of equality. So it doesn't seem obvious to me how you would build up a semantic
equality
model
type we
for
based
both of these
on
equalities.
is the intentional version of Martin-Löw type theory. And the hybrid equality is a subset of usual full term equivalence. So I don't know. I have to study more carefully. But yeah.
Maybe one more quick question while the next speaker sets up.
So you have an assumption that says that constructors are at the same time at all stages. How do you think you can lift that? Because this is the easiest way to get MetaOCaml to crash. You can make this assumption false.
Constructors and constants are kind of primitives of the language. So